Okay, so now this is the second part of chapter 11. Now in the previous part we talked about doing a test of hypothesis for a population mean if you have a small sample. The main difference between the small sample and the large sample was that you will use a student t distribution and the t statistic instead of the standard normal distribution and the z statistic. Okay, but the formulas you noticed are very similar. Actually, you can see that confidence interval for the mean mu for small samples is also very similar to the large sample case. Only difference is that the z value in the large sample confidence interval has been replaced by the t value. Okay, now for the t, of course, we have an additional parameter, the degrees of freedom. So degrees of freedom is in -1, and then you need to get the 1 minus alpha second percentile. Remember, 1 minus alpha is like if you have 95, 1 minus alpha will be like 0.95, and then 1 minus alpha by 2 will work out to be 97.5. Okay, so 97.5th percentile for degrees of freedom in -1 will give you this value. Okay, all right, so it is the same as the point estimate plus or minus, margin of error. Typically margin of error, the term is used for 95%. That's pretty much what it is. And actually you can apply this formula for any estimate. You will learn if you do a course later. This works for any estimate, and even the statistic formula will work for any estimate. In fact, I may write it somewhere so that you guys will know about it. Okay, all right. So similar procedure. You just get the t value from the table or from the software. You plug them in, you get the confidence interval. That's pretty much what it is. So we are done. Okay, let's see. um, so here's a example. So to calculate a 95% confidence interval for the mu, which is the actual birth weight of 6 babies. Now here we have a sample of 10 such babies. We found the sample mean to be this, standard deviation, plug them in. Now see, the degrees of freedom will be 10 minus 1, which is 9, and then 1 minus, when you figure it out, this will be 97.5, and you can look up for degrees of freedom 9, what the t value is. If you have 0.975, then you will get this 2.2762. Okay. And now of course, remember in the t table, they yeah, let me see, they give in terms of, I just want to say something. Yeah, so if you look in here, so this is what it is. See, the 97.5th percentile is cumulative p is 0.975, so the t value is 2.262. You can look it up in your tables also. Okay, so that is how that value of 2.262 was plugged in that slide. Let me go to that slide again. Yeah, right here. Okay, so that 2.262 is the t value if you have the cumulative p to be 0.975. How did I get 0.975? 1 minus 0.052 over 2. 2 will work out to be 0.975. Okay, 1 minus 0.05 over 2. 0.05 over 2 will be 0.025. Okay, all right. So then you do the math or the algebra, and then you get this. So which means you can say that you're about 95% sure that the average birth weight for 6 babies, that is the population birth weight, would be between 2,300 to 3,400. See, now look, remember the relationship between hypothesis testing and confidence intervals. Remember our mu sub 0 when we did the test of hypothesis, it was 3,300. See, 3,300 is in this range, right? So that means that, so remember, if the mu sub 0 is in the range, that means you will go with H0. It's not easy. It is not good for us to reject it. Remember, we said that that was a gray area that the chi value fell in. We cannot really go against H null. So the same conclusion can be arrived here. Okay, 3300 is almost to the borderline. Okay. All right then. Okay, so the next slide, another example. Okay, so here there are 18 diabetic patients. Their body weights are given. So if you calculate it real quick, you can plug this in, and then you'll get x bar to be 112.2778. Standard deviation n is 18. Then you can figure out the standard error. Again, you plug them in the formula. You will get this confidence interval. Okay. You can as practice, you can see whether whether this is indeed the value with degrees of freedom 17. How did we get 17? 18 minus 1. And then 95 means 1 minus alpha by 2, which is the left probability is 0.975. Okay, easy, really easy once you do this. If you know to do one particular situation, doing the others is not that difficult at all. Okay. Okay, so now here's another new idea. Okay, now paired samples. Now this is a very important idea or a design or experimental method that's quite helpful in health studies. Okay, now so it's called paired samples, and sometimes it's called matched pairs and dependent samples also. All these terms mean the same thing. Now, when do you do this? You will understand what this is all about. You will do this, if there is another external effect, another second effect that you need to control. Okay, and what you do is, how do you control it? You will match according to that external factor. Okay, so here let me go with the example here. Say the purpose is to examine the difference in birth weights between male and female babies. Okay, so when babies are born, you have male babies, you have female babies. Typically, so the interest may be, okay, are the male babies bigger in weight than females or the other way around? Okay, so now, but you can see that, okay, just if you just take a bunch of male babies and a bunch of female babies and get their averages and compare, you can even see that's not going to be working well, because there are so many different issues that plays a role in birth weights, not only gender. So that's what I'm saying here. Birth weight depends not only gender, depends on not only gender, right? Um, you know, One factor could be ethnicity. Another factor could be the economic status of parents. There are a lot, and then all the smoking status of the mother. All kinds of things plays a role in the birth weight. Okay, so here, just to make things simple, I just considered only one external factor, which is ethnicity. Because see, why is it called external? We are not interested to see whether white babies are heavier than Asian babies. Okay, we are interested to see whether male babies' weight is different from female babies. Okay, so ethnicity is not the factor that is of importance to us, but it plays a role. So this is an external factor which plays a role on weights, birth weights. Okay, so we need to remove the effect of ethnicity so that we can look to see you can look to see what is the exact pure effect of gender with regard to birth weight. So what you do is, instead of randomly selecting male babies separately from female babies, you will try to match each male baby or each female baby with a counterpart male baby who are from the same ethnicity. So you can have different, maybe 10 or 15 baby pairs, each one being male and female, but in each pair, in each pair they will belong to the same ethnicity. Okay. Oops. And then once you do it, then what you do is, so across, so you will have a pair of bits. So you'll have a row of pairs, and then you will have two measurements for each pair. You will take the difference. Once you take the difference, that difference actually reflects the pure gender effect on birth weight. Think a little bit, right? So that is the idea behind paired samples. Paired or match, you match them or pair them according to this external factor. Here I considered ethnicity. Now there are lots of other things that that plays a role in many measurements that is of interest in biostatistics. Okay, so here there's gender, which is of the major importance to us. Ethnicity is a secondary effect which is not of importance to us. So you need to remove the ethnicity effect. Okay, all right, let's do another example here. Now here, okay, now this is whether oat bran reduces LDL cholesterol. Okay, now this is called a crossover design. Crossover design means, okay, you will give the same, see now you have to compare like oat bran with another usually traditional maybe diet like cornflake diet or something. Okay, but see now crossover means you give both these diets to the same person. Okay, but of course there's something called a washout period, so that you will remove the effect of the first diet. Okay, so first diet was whatever the first diet is, and then you will have a washout period, that means just a neutral period, and then switch to the second diet and then give the second diet. Okay, now see, and then you will give both these diets to the same person. Now what is the external effect here? This is a paired sample situation. Now we are interested in the diet difference, right? How the diets play a role. How is there a difference in diets towards cholesterol? Okay, so like birth weight in the previous example, LDL cholesterol is what is in this example. Okay, in the previous example, gender was of primary importance to us. In here, the diet difference. Now here, when you take the same person, the external factor is actually the person-to-person effect. Okay, because see, we all differ. So now, if you give diet 1 to one bunch of people and then diet 2 to another bunch of people, you have not control for their personal effects. But here, if you give both the same, that means you are not being fair or unfair to either diet. You are giving both to the same set of people. Okay, and then you have a washout period to sort of neutralize the first effect, the effect of the first diet, right? So now here's how the data will look like. Oops, it's in blue, but anyway, look closely here. So you have subjects. Subjects are like people. So you will have the cholesterol with the cornflake and then cholesterol after the oat bran. And then now see, if you take the difference between these two values, like the first value is 4.61 and then 3.84 from subject 1. So if you take the difference, now that difference is a pure reflection of the diet difference towards cholesterol. Okay, so let's go to the next slide. So that difference now is called delta. So now rather than deal with the cornflake cholesterol level and the oat bran cholesterol level separately, we created a new one variable. Here you have two columns of data. From two columns of data, we created one variable, one column of data, delta. This is what we want. We are working with delta from this point on. We don't need these two columns anymore. Okay, we don't need these two columns anymore. We will need this only. Okay, so you have delta. Now see, delta delta is positive, means the oat bran cholesterol level has been more. Delta is negative, like in here, means cornflake cholesterol level has been more for that patient 3 or subject 3. Okay, that's what it says in this box. Okay, now actually delta is just one variable, right? It is it's actually not, it is really the same as x values which we studied in one sample situations. Okay, so we created from a two sample a one sample situation. Okay, So now we work with delta. Okay, delta is the difference. So now, so if you have the deltas to be this, n equals 22, now we can calculate the x bar for d. Now see, d means we are working with deltas, but of course it is just one individual value, one individual variable. But just to say that we are working with differences, the subscript is there, then again you can find the SD, which is the standard deviation of this data. Okay, and then of course you can apply the t statistic and the confidence interval for mu for small samples, because you know n was small. Remember what was n? N was 12, right? So then you can figure out the confidence intervals values. So what this says is that okay, the entire confidence interval is positive. So now remember, how did we get delta? We just go back in here. We got delta to be cornflake minus oat bran, right? Yeah, cornflake minus oat bran. Okay, so what this means is, so let's go in here. So what does this mean? So this is like delta is, okay, I'll just write it in here so that we will understand this. Delta is cornflake minus oat bran, right? Now look, the entire confidence interval is positive. See, this boundary which is the left is positive. This is also positive. Obviously, if this is positive, this will be also, because this is to the right. That means cornflake cholesterol after cornflake is more than the average cholesterol level after oat bran, right? So I'll say the entirely, I'm just writing it here, entirely positive confidence interval implies that the mean cholesterol level, oops, I'm making mean cholesterol level with cornflake diet is more, right? So oat bran is good for cholesterol, right? Okay, so that's how how we can come to conclusions using confidence intervals. Okay, so pair t-test. Now you can do a test of hypothesis also like that. So again, remember, see, these are like one single measurements. Now you will test mu equals 0. Now mu here is the difference. Okay, maybe I should mention in here. Mu here, mu is the mean difference. Okay, mean difference. So this mu here stands for the mean of delta. If the mean is 0, right? If the mean is 0, that means there is no difference between average cholesterol levels between the two diets, right? So now how do you test it? If you want to do a test of hypothesis, you will plug x bar d, which we calculated from the sample, mu sub 0, and here it is 0. SD we got from the sample, n we know. And then you plug this in and then do the test of hypothesis just like the way we did earlier. Okay? Alright then. So now, so we got the actually once by plugging that now, so in fact, see, they have mentioned mu d. Mu d means mean, mean, mean difference. Okay, and then the t statistic will be 3.043, and then we get the degrees of freedom to be 11, and then for this t statistic we will get the p value to be 0.011. Of course we can get it to accurately using a computer, that means software, or you can get it approximately using a table. And then so if p is 0.01, that means this is kind of small enough, isn't it? Even at alpha equal to like 0.05, so which means it's okay for us to reject H null. Okay, the data is telling to go against H null. H null says there is no difference. Okay, so which means we will go with mean is not equal to 0. So in fact, the same conclusion that we got from the confidence interval. The confidence interval was entirely positive, which said that mean is non-zero. Okay, so it's a similar result that we get here. Okay. Okay, now this is like see, if you do this using a statistical software called SPSS. CSPSS is a statistical software. You will get a output like this. Okay, if you do the one sample test. Now this SPSS is very widely used in public health and medicine. So it's good to sort of be familiar with it. Now one thing is, see, now this is the t statistic value. This is the degrees of freedom. Now in SPSS they have sig. Sig means p-value. So sig stands for significant. Okay, so if you see sig, and this is a two-tailed sig, means two-tailed p, and then they also give you the 95% confidence interval. They give other summary statistics as well. Okay. Okay, now conditions for inference. Now t procedures. Now typically to do the t statistic, of course you need to have SRS. SRS means individual observations should be randomly chosen. Okay, so that's what it means. Okay, let me write it down. We did not really talk about different kinds of sampling methods, but this is what it means. So this simple random sample means the data is chosen in a very random way, so that you'll be fair to every unit in the population. Okay, and then information is not biased, so that that means the sample is well representative of the population. Now this is something important. For the t procedure to work well, you have to have the individual x values to come from a normal distribution. Okay, see, this bullet 3 means individual observations or the delta. See, if you do the paired test, the deltas, if you do the individual x, then individual observations, that means x, right? I'll just put that in here. So you need to assume. See, we do not know, because we have only a small small part of the data, like n will be less than 25. So even to get the shape like in a histogram, that is not enough. So this is actually an assumption more than even a condition. This is an assumption because we are not in a position to check this. Okay, but the t statistic works if the x or the deltas are normal. I mean, if you are working with x's have to be normal, or the deltas have to be normal if you are working with matched pairs. Okay, now it's so it is a condition which we cannot even check. Okay, so now there are rules of thumb. Okay, now ideally if x's should be normal. Okay, if x is normal, if you sort of have a symmetric distribution with at least 5 to 10 observations, it should be okay. Now see, how do you check for symmetricity? You can check for symmetry using, you can histogram, of course, small number of observations not enough. You can do a stem and leaf. Even box plot would be okay. You can see whether the median is right in the middle. Check using. Okay, so if you have a symmetric distribution, even if it is not normal, if you have at least 5 to 10, it's okay. Now if the population is skewed, again you can check it by using a box plot or even a stem and leaf. You need to have good number of observations. Okay, All right then, 30 to 100. Of course, if you have 30 to 100, you can use the Z table, don't you? Um, because even if the individual population is skewed, remember the central limit theorem. It says that if you have n to be large, x bar is normal, and we can use the Z statistic. Okay, so let's look in here now. Okay, so these are like 3 different examples where they have given stem and leaf. So you have ages of grad students. Now this is skewed, right? um, so you have to avoid t distribution because the data number of observations is also really small, skewed. And then how many observations are there? Two. Let's see. We have 1 2 3 4 5 6 7. That's all, right? So 7 is not enough if you have a skewed distribution. It has to be 30 or more, right? Now this one is pretty okay. It's mildly skewed. Okay, and sort of symmetric. So and then the sample size is not bad. N equals 25. Oh, here n equals 6 they give. So for this it's okay to use the T procedure. Okay. Now here you have a large. Let's see, n equals 13, but again it is skewed, right? So because that avoid. Okay, so by looking at the stem and leaf, you can sort of get an idea whether T procedure can be used or not. Okay. Now that is the end of exam material. Then the remainder you have calculating power. Okay, sample size and power. Now see, I won't hold you responsible for these slides, the remaining slides, but I will have them in the presentation. If you are interested, certainly you can look at them. But the sample size, I will have formulas, but the power I will not have. I will not have anything even in the formula sheet. Okay, but when we do problems, of course, at least for the large sample case, we will learn how to calculate the sample size. Okay, if we have time, certainly. Yeah, actually we will do the sample size for the large sample case, because you cannot do for the small sample case, because without knowing n you cannot do degrees of freedom, so you cannot refer to a T table, so you always have to work with Z. Okay. So again, to tell you, now I put a slide in here. So right at this point, the exam material stops. Okay, from this point on, there are few slides. It's about power. If you're interested, certainly go over it, and you can discuss with me. Whatever time you please. Okay, all right then. Thank you.